Mummy, there's no plane up in the sky.
Jersey 9 November Victor, runway 27 aligned, wind 27018, cresting 32.
Still 37 Jersey 9 November Victor.
Emirates 148, hello, behind Air France, line up 24 Sierra 7 behind.
Behind the Air France, line up runway 24 behind Emirates 148.
Hello. Today's presentation is entitled Tracking Commercial Aircraft in Near Real Time using a Raspberry Pi, Kafka and Vertica. This presentation provides a summary of a project which has been evolving over the past year in conjunction with a number of big data and machine learning meetups. This project is the first of the lab series where we look at automatic dependent surveillance broadcast to track the movement of commercial aircraft in near real time and seeing what we can do with this data. My name is Mark Worley and I am a Vertica systems engineer within the Micro Focus organization. I will start off by giving a brief introduction to the Big Data and Machine Learning meetups and the lab series. Then moving on to discussing the first project in the lab series, providing a high-level overview of automatic dependent surveillance broadcast and how, using a Raspberry Pi and some open source software, we can capture and decode the ADS-B radio broadcast signals. With a continuous stream of data, we then look at using Apache Kafka as a messaging bus, being fed with messages via an ETL process. Next in this project, we look at capturing this streaming data in a Vertica database. However, before jumping into this, I will provide a brief introduction to Vertica, followed by the inbuilt integration with Kafka and its management console for monitoring and managing the Vertica Kafka streaming. We then touch on some of the many third-party tools which integrate with Vertica, demonstrating some of the simple visualizations of the captured data. As the project moves towards discussing advanced analytics and machine learning, we look at some of the data modeling tools built into the core of Vertica, touching on data capture and enriching, measuring and preparing, and in future presentations where we will look at modeling and deploying advanced analytics and machine learning. This presentation concludes by looking at three of the many measure and prepare functions of outlier detection, gap filling and interpolation, and sessionization. Finally, a single slide to highlight what's next in this project. With a background covering many database technologies, from Michael Stonebreaker's Ingress row store database management system through to Stonebreaker's highly performant advanced analytical column store Vertica database, back in December 2016, I established the London Big Data and Machine Learning Meetup Group. The primary goal being to bring together people with a shared interest in anything related to big data and machine learning and the surrounding ecosystem, regardless of technology, background, or experience. With 1,500 members and growing, we try to meet once per month where we have presentations and talks covering a wide and varying set of subjects and give members the opportunity to network and discuss what they are doing in the world of big data. With the London Meetup Group now well established and having recently relocated to Campus London, we have since established another group in Munich where I'll be presenting in November this year. Then just a couple of weeks ago, we held our inaugural Cambridge Big Data and Machine Learning Meetup at one of our Vertica customers, Jagex, in the Cambridge Science Park. Having attended many other technical meetups, a common theme seemed to be that at each event there would be one or more talks. However, other than sharing a common theme of the meetup's purpose, each of the talks is typically delivered in isolation to any other presentations. Although we wish to encourage and promote such talks in our Big Data and Machine Learning meetup, we also wanted to introduce a thread that would follow through from one meetup to the next. We entitled this the Lab Series. In this, we would incubate a series of mini projects. The subject, technology, and direction would be determined by the group's members. We would ensure that at least one presentation slot at the meetup event was reserved for those mini projects, where members would report progress with their project. But possibly more importantly, we wanted to ensure that these projects were inclusive to all. Anyone who wanted to be actively involved or simply follow the progress of these projects would be encouraged to do so. With the inaugural Big Data and Machine Learning meetup in London, and not having been able to present this idea behind the lab series to our members, we were in a typical chicken and egg scenario. So, to start the ball rolling, I proposed the first mini project. Picking a subject that I knew absolutely nothing about, I decided to opt for one called Automatic Dependent Surveillance Broadcast, or ADSB for short. Not that abbreviating it makes it any easier to understand what it is. Contrary to popular belief, it's not always raining in Wales. Sometimes the sun does shine. A little while back, while sitting in my back garden, I was staring aimlessly into the sky, watching the condensation trails being left by aircraft flying high above. This then got me thinking about those small silvery dots in the sky, where those planes had flown from and where they were flying to. How fast were they travelling? What is their altitude? What is the type of plane? Who is the aircraft operator? And why am I not on that plane travelling to some exotic location? I then started to wonder why in the mornings there were more flights travelling from west to east, and in the afternoons from east to west. Back on terra firma, our highways have designated lanes. We drive on one side of the road, usually, and have various traffic management measures: traffic lights, speed cameras, roundabouts, junctions, road markings, and signs to guide us. Up in the sky, there appears to be nothing that keeps those 300-ton conveyances travelling at 500 miles per hour from bumping into each other. What's more, although planes have ABS, like most modern cars, it's not much use at 40,000 feet, nor does turning the wheels of the landing gear to avoid a collision. My curiosity had been stirred, and I had to find out more. Using my best friend and font of all knowledge, I used Google to start researching the subject. First I looked at primary radar, then secondary radar. I then came across a relatively new innovation called Automatic Dependent Surveillance Broadcast, or as I said earlier, ADSB for short. Although a far more complex subject matter than I can give justice to here, in summary, ADSB relies on transponders in aircraft receiving and transmitting digital broadcast signals via the radio waves. This is further enhanced by accurately identifying the position of the aircraft by means of satellite navigation systems. The data being broadcast includes the aeroplane's call sign, registration number, altitude, speed, longitude, latitude, squawk, and other details. These transponders, as well as responding to requests from ground-based stations, automatically transmit their details several times per second. The name Automatic Dependent Surveillance Broadcast comes from automatic in that no pilot or external input is required for it to operate. Dependent, that it depends on the aircraft's navigation system and other components. Surveillance, for determining its position via satellite navigation and then used for tracking. And broadcast, that the data is broadcast over the radio waves. ADSB is transmitted at a frequency of 1090 MHz and can be received by any radio receiver that can capture that frequency and software that can decode the digital broadcast signal into its representative usable data. In addition to being used by air traffic controllers and by the aircraft's own navigation systems for collision avoidance, a number of other uses of ADSB data have sprung up. One such example being organizations such as Flight Radar 24 that you can see here. These rely on thousands of contributors around the world who have set up their own equipment to capture and decode the ADS-B signals from aircraft in their locality. These contributors then make their data available via the internet to the likes of Flight Radar 24. They then make this data available via their flight tracking website to anyone who is interested in seeing the movements of aircraft around the world in near real time. Having seen what is possible, I decided I wanted to get more involved in this and find out how to set up my own ADS-B flight tracking facility. Further research, and I came across a number of options. After some consideration and wanting to keep this mini project accessible to all, I settled on picking a Raspberry Pi. There were two pressing factors which swayed my decision. Firstly, it's cheap. Secondly, just as importantly, it is built in Wales, my home country. The next piece of hardware I needed to source was a digital broadcast receiver. I soon came across another inexpensive piece of kit, a USB DVB-T DAB TV receiver, designed to enable you to watch digital terrestrial TV on a PC or laptop. However, this £10 to £15 receiver just so happens to have a chipset that, as well as capturing the frequency required to watch terrestrial TV, also covers the 1090 MHz, just what I needed to capture those ADS-B signals. In addition to the USB dongle, the kit also comes with a 6-inch antenna. This is perfect for capturing strong signals from aircraft close to the receiver. However, if you want to capture weaker signals from aircraft further afield or where atmospheric conditions restrict signal capture, you may wish to replace this with an antenna purpose-built for capturing the 1090 MHz frequency. Of course, the easy option would be to buy one of the commercial offerings. However, at a cost of more than a couple of times the Raspberry Pi, I decided to investigate how to build my own. Further research, and I came across a number of websites that described how to build a DIY 2-meter coaxial collinear antenna. A few hours later, and with the antenna housed in a 15mm plastic water pipe and the USB dongle in a pink Vanish washing powder container, all secured with plastic cable ties, the antenna was mounted at the highest point that I could on the roof of my house and in sight of Swansea International Airport. The Raspberry Pi, housed in a plastic box, connected to a 1TB USB disk drive, again held together with a pair of plastic cable ties and connected via two 15-meter USB cables to the USB receiver, the hardware was all set, and at a relatively low cost. Having now delivered this talk at a number of venues around the world, I also decided to build a portable Raspberry Pi with its own home-built casing, using some free offcuts of clear and white perspex. As you can possibly imagine, getting this through security at airports has been quite an interesting challenge. I'll refrain from discussing this here, but if you want to know more, let me know. With the hardware assembled and Linux installed, patched and updated, it was now on to an open source piece of software called Dump 1090 for decoding the ADS-B signals being received. The text shown here is a snippet from the README from GitHub. In addition to decoding the ADS-B signals, two other important features of this software are the TCP stream of messages via the default port of 30,003, some more of this a little bit later. The second is the HTTP server that displays currently detected aircraft on a Google map. Although this is not so important as we delve deeper into this project, being able to have a visualization of the aircraft currently being picked up is useful to confirm that the primary data capture and decoding is working. Without this, there's not much point in continuing until it can be proven that the messages are being received and, of course, decoded. As mentioned on the previous slide, one of the outputs of Dump 1090 is the Google Maps display of currently observed aircraft. My receiver is located on the Gower Peninsula west of Swansea in South Wales, in the UK's first area of outstanding natural beauty. Not that I'm belittling all the others that became AOMBs after hours. In this 5-minute time-lapse image, I have highlighted one flight, BAW 827. I first captured signals from this aircraft over Anglesey in North Wales, and 5 minutes later it was flying over Birmingham. I suspect it was about to join the M40 down towards London and no doubt catch the traffic on the M25. In that 5-minute window, I received 7,500 messages from that single aircraft. That's approximately 25 messages per second. Multiply this by 50 for each of the aircraft that are being picked up by my receiver in South Wales at this time, and I trust you can see that there is clearly a pretty good source of real-time streaming data, and perfect for our project where we want to prove streaming data capture into a database and then to investigate what we can discover from this. One of the other outputs of Dump 1090 is the streaming of messages on TCP port 30003. Using Netcat, or as I am here, NC, from port 30003 of the local host, we can see the continuous stream of messages being presented. Each message is identified by a message type, here seen as message 1 through to message 8. We can also see the aircraft's International Civil Aviation Organization's 24-bit address, often referred to as the Mode S or hex ident. Timestamp the message was generated by the transponder, altitude in feet, longitude and latitude, speed above the ground, heading, and the final field indicating whether the aircraft is on the ground, 1, or in the air, 0. As can be seen here, with my transponder being located west of Swansea and with not many Airbus A380s landing in Swansea International Airport, just a few private planes, hand gliders and parachutists, it is rare for me to see anything other than 0. Supplied here mainly for reference, you can see the various message types that are picked up by the receiver. These include extended squitter information and category and surface and airborne position messages. Each of the message types deliver a varying number of fields, 22 in total. Some of these fields seen here include the hex ident and date and time the message was generated. And here we have the call sign, speed, track, longitude and latitude amongst others. Each message type reports a different set of fields. As can be seen here, for example, message types 2, 3, 5, 6 and 7 include the altitude, whereas 1, 4 and 8 do not. In the time that an aircraft's signals are within range of the receiver, one would expect to receive most, if not all, of the message types, with some being received many tens, hundreds, or possibly thousands of times. With message type 1 providing the call sign, such as BAW 827, a series of other time-stamped messages providing altitude, longitude, latitude, and speed enables us to build up a complete picture of the flight path for each aircraft. Apache Kafka is an open-source, distributed stream processing platform. Kafka topics store streams of messages from producers along with a timestamp and a unique incrementing offset in one or more partitions. Consumers can then query the messages from the topics partitions. With this, Kafka provides a real-time streaming data pipeline that can reliably pass data between systems or applications. In our case, I wanted to be able to pass the stream of ADSB messages from the Dump 1090 application through to the Vertica database where these messages will be stored in the database tables. However, not looking for high availability or high performance within the messaging bus, I wanted to keep this project as simple as possible. I decided to define a single partition for each topic, with one producer sending the separate message types to each. Further down the line, and covered on subsequent slides, there will be a consumer picking up the messages from each topic and loading the data into Vertica tables in microbatches. With messages being delivered on the TCP port 30003 and the series of Kafka topics having been defined, the next task was to set up an extract, transform and load or ETL component to join these two pieces together. Of course, many off-the-shelf ETL applications I could have selected, or of course I could write my own, which is what I decided to do. I naturally had a choice of programming languages, including C, Python and Java. I opted to write mine in Bash with lots of AWK. The 1300-line script, along with other snippets of code, have been published on GitHub for those who want to repeat this project for themselves. In summary, the ETL script captures the stream of incoming messages from the TCP port. It then extracts the individual messages by message type and performs some simple transformation, adding a location field to identify where the Raspberry Pi and the receiver are placed, and reformatting the separate date and time fields into a single timestamp field. Next, the messages are fed into a series of message buffers where the open source Kafka Cat utility picks them up and writes them to the individual Kafka topics. For reference, Kafka Cat is a generic non-JVM producer and consumer for Kafka. With the ETL process hopefully running in background, it is advisable to check that it is working as expected. For this, we can use Kafka Cat in consume mode to observe the messages that are being fed into a single topic. For those familiar with Linux, it's like running a tail-f on a log file. This will show all the messages as they arrive, pausing and displaying the latest offset as it waits for the next set of messages to be posted. Here we can see the messages in message 1 topic up to an offset of approximately 11 million. With our source of streaming data being fed into Kafka topics, we next want to load this data into a database such that we can start to investigate what we can do with it. Of course, we could pick almost any database technology to achieve this, but I can think of none better than Vertica. The following couple of slides provide a very high-level overview of Vertica. For more detail, it can be found on visiting vertica.com or, of course, contacting me. With its thousands of customers worldwide, it is often surprising how few people have actually heard of Vertica. Though when you see some of the names of our customers, such as Zynga, Twitter, Uber, Facebook, and Etsy, enterprises driven by data, the reasons they have chosen Vertica will soon become apparent. Back in the 1970s, Michael Stonebreaker and colleagues at UC Berkeley designed and built the world's first row-store relational database management system, called Ingress. Later, and realizing how the volume, velocity, variety, and veracity of data were starting to explode in the industry and had pushed row-based technologies to their limits, Stonebreaker co-authored a paper entitled The C-Store, a column-orientated database management system. In 2005, he went on to be one of the founders of Vertica, a massively parallel processing column store analytical database designed from the first line of code for the world we live in today. With storage and retrieval of data in columnar format, this enables Vertica to deliver extremely high performance when executing complex analytical queries on huge sets of data. With data stored in columns, Vertica is also able to aggressively compress and encode its data unlike any row store technology, not only greatly reducing costly disk I/O to boost performance, but enabling Vertica databases to be stored in a much smaller footprint, hugely saving on operational and hardware expenditure. Its MPP scalability means clusters can be expanded and contracted without database downtime, and with its distributed query capability allows any node in the cluster to be the initiator of a query and all nodes contributing to its execution. Designed so there is no single point of failure, unlike other solutions with their leader or master nodes, and with its projections providing for optimizations of query performance and high availability built in, unlike others who added high availability as an afterthought. Clearly, Vertica stands out from the crowd, and no wonder the likes of Zynga, Twitter, Uber, Facebook and Etsy, amongst many others, selected Vertica as their database of choice. At its core, Vertica provides a toolbox with just about everything one could ask for. Whether that be real-time analytics, event and time series, geospatial or machine learning. And where users want something not found in the box, there's the ability to create user-defined functions written in Python, C++, Java or R. With its open architecture integrated with rich ecosystem, Vertica sits beautifully with hundreds of third-party tools for data transformation, messaging, ETL, BI and visualization. Where your data already lives in Orc, Parquet, Amazon S3 or Hadoop, this is no barrier to Vertica. Data can be analyzed in place via external tables, or where greater performance is required, that data can be ingested into Vertica. Want to deploy on-premise? Not a problem. Build yourself a Linux cluster and away you go. Put your heads into the clouds and your database too? Not a problem. Vertica can be deployed in AWS, Azure or Google Cloud. Want to sit alongside the elephant? Then deploy Vertica inside or alongside your favorite Hadoop distro. Okay, that's enough of the sales and marketing pitch for Vertica. Let's get back to this project. With our Vertica database installed and up and running, we now want to see how to ingest the Kafka data into the tables within the Vertica database. Fortunately, Vertica provides a very handy command line interface to define the various components to integrate itself with Kafka. Firstly, there is the scheduler. This continuously loads data from Kafka into Vertica, cycling around by default every 10 seconds to process any new messages waiting to be loaded into the database. The cluster configuration identifies the Kafka broker or brokers which house the Kafka topics. Then the source and targets define the Kafka topics as the sources and the database schema and tables as the targets. Next we define the load specification, including the data format. There are many supported load parsers, including JSON and Avro, or, as in my case, a simple CSV format. The microbatch configuration joins together all the various components, the cluster, the relationship between source and targets, and load specifications for each. Part of the Vertica toolset is the Management Console, a graphical user interface. One component of this is a section which reports the current status of the Vertica Kafka integration. Zooming in on this, we can see the individual microbatches, Kafka sources, Vertica schema and table targets, and the timestamp the last microbatch ran, defaulting, as I say, to every 10 seconds. To the right of this, we see the number of messages processed in the last microbatch and last hour, and the total number of rows that were accepted and thus loaded into our target table, and the number of rows which were rejected. Drilling into rejections, Vertica provides a reason for the rejection. Here we can see that the data was rejected as a value of 51.60 was supplied for a column that is defined as an integer. A question often asked is, how many rows can Vertica handle from Kafka? How quickly can it load that data? Although not a very scientific test, I decided to reset the Vertica scheduler and let it attempt to load all of the messages that were waiting in the Kafka topics from the beginning. As can be observed on the right, under the end reason column, there are now two different messages. The end stream implies that all the messages waiting to be processed for that topic were handled within the microbatch window, here set to 10 seconds. The deadline reason indicates that Vertica was not able to process all of the messages waiting to be processed and ran out of time. Of course, Vertica will pick up from where it left off for these deadline messages, and resources permitting will in due course catch up with the backlog and return to a full house of end of stream reasons. So, as I said, not very scientific test, but this gives an indication as to how far I can push the available resources. Totting up the total number of messages that were processed in that 10-second microbatch window, we can see that we managed about 814,000 messages. To which those who asked the question would typically say they were not impressed, expecting far more to be loaded. Scaling up, that's about 4.9 million per minute or 7 billion per day, to which they are still not impressed. Then I remind them what resources I was using. A single core, half a gigabyte of RAM Raspberry Pi running the Dump 1090 software. A second Raspberry Pi running the ETL process at Zookeeper and Kafka, and a laptop with 8 cores and 16 gigabytes of RAM running CentOS 7 and a single node of Vertica. To the other extreme, we then looked at a couple of our customers, Facebook and Vertica. Ignoring for the moment what Facebook managed to achieve, Vertica managed to get a sustained 2.42 billion rows, that was approximately half a terabyte, loaded into a Vertica via Kafka and Spark in just 7.5 minutes, using an 8-node Vertica cluster. They then went on to reach 36 terabytes per hour using 81 nodes. So I trust this demonstrates that Vertica can achieve some very impressive streaming loading of data via Kafka if you have the appropriate resources available. For me, I'm more than happy with my Raspberry Pi's performance. As mentioned earlier, Vertica sits very comfortably with hundreds of third-party integration tools, a small number of which are shown here, whether that be infrastructure, cloud, BI visualization, OEM, Hadoop or data integration. Now that we have data streaming into the database and with historical data accumulating without limits, other than my laptop running out of disk space, we then went on to demonstrate how simple a process it is to connect one of these tools to Vertica and be amazed by its performance even on a single node of instance of Vertica running on my laptop. Of course, whenever I present a slide such as this, someone in the audience pipes up to point out that their product isn't listed. And when I then pick one to do the demonstration, I get reprimanded for not picking theirs either. Unfortunately, there's only so much space on the slide and so much time I have to do the demonstration, so I can but apologize. In this simple visualization, I decided to plot altitude and number of messages I had received for each. As mentioned previously, this Raspberry Pi is located in my home office west of Swansea. Here I get to see many of the transatlantic flights. These are typically flying between 30 and 40,000 feet when I see them. There are a small number of flights between 15 and 30,000 feet. These are probably flights taking off or landing in Cardiff or Bristol to the east of me, or maybe Cork to the west. For the more eagle-eyed of you, you may spot some aircraft reported as flying at up to 110,000 feet. Now that worries me. However, what worries me more are the aircraft that appear to be flying below sea level. Clearly, there are some data quality issues here which we would need to address if we intend to use this data for building machine learning algorithms. More of this in a little while. With longitude, latitude and altitude available to us, let's start to look at flight tracks. This only touches on some of the geospatial capabilities of Vertica, and again, something we'll be looking at further as this project develops. Expanding the previous slide to show altitude as well as longitude and latitude reveals something else. Although not possible to pinpoint here, the Raspberry Pi and receiver are located just under that central, lighter coloured aircraft set of tracks. These lower flying, lighter coloured tracks are probably from aircraft that have taken off from Swansea Airport or are other low-flying aircraft such as helicopters or private single-engine planes. What is interesting here is that I do not see these aircraft any further away. I'm fairly sure they're not circling my house, so it's either down to their low-powered transponder signals that I'm not able to pick them up as they travel further away, or, as I need line of sight between antenna and aircraft, that the lay of the land and surrounding buildings is preventing me from receiving their signals. Although I need to investigate this further, I am wondering whether it is possible to determine the topology of the land from the ADS-B signals. Picking on just one scheduled flight, Aer Lingus flight STK-43BR from Bristol to Cork, this flight is now operated by Stobart Air, and I thought they just carried cargo up and down our motorways. As can be seen here, the majority of the flights follow a similar tracking, although there are clearly some that deviate off this well-worn track, not that tracks get worn into the sky. What I hope to be able to do when investigating this data further is to try to determine why some flights do not quite follow the same route as seen from the other flights. Is it weather related? Was there an emergency elsewhere that forced the pilot or air traffic control to reroute the flight? Or did the autopilot just get lost? There could be many reasons, and it is hoped that by building up this data we will be able to dig deeper into understanding some of these anomalies. As well as using the off-the-shelf visualization tools, although I am no expert in designing web interfaces, I thought I would try my hand at writing some code. Starting with good old bash shell script and with some embedded SQL to pull out the latest positions of aircraft from the Vertica database, then dynamically writing some HTML code with references to a Google Maps API. We then get to a display which has some similarities to which I first saw with Flight Radar 24. Though this time the data has been captured by the digital broadcast receiver on the Raspberry Pi, decoded using dump 1090 before being fed into a series of Kafka topics. From here, the data gets ingested into a series of Vertica tables from the Kafka to Vertica scheduler. Then, once every 30 seconds, a cron tab script will fire up to run this shell script to build a HTML script with planes plotted using a Google Maps API. Not the most professional of looking at displays, but not bad for someone who lives and breathes green screen character-based putty. Following on from looking at some of the third-party tools that integrate with Vertica, the project moved on to looking at some of the many analytical capabilities of Vertica. Ignoring the functions that one would expect of any mature SQL database, such as aggregates, analytical and Windows functions, we started to look at the SQL extensions. These include pattern matching, event series joins, and time series. We will soon move on to looking at the SDKs, which can be built and deployed using the programming languages of C++, Java, Python, and R. This will then lead on to looking at some of the in-database analytics, including linear and logistic regression, k-means clustering, random forest, and more. For now, we're going to concentrate on three of the measure and prepare functions, namely time series preparation, gap filling and interpolation, sessionization, and outlier detection. You'll recall the earlier slide where we plotted altitude and number of flights. When preparing our data for machine learning, although we may be concerned about anomalies for other reasons, such as why are we picking up messages from aircraft that appear to be flying below sea level, we need to find a way of excluding such outliers when building our models. With much of the time usually spent in preparing data, it would of course be so much easier if a simple to use function was available within the database toolbox to achieve this for us. Before we look at such a function, let's take a closer look at our data. Here we are just counting the number of rows in our message 3 table. Just under 150 million rows. Taking a closer look at a typical aircraft, here we're looking at hex ident 00B203 on the 27th of June. The first time we see this aircraft is at 18:59 and 31 seconds, flying at an altitude of 19,000 feet. with subsequent messages at 32 seconds, then 38, 40 and 43. It appears that this aircraft is climbing as its altitude is increasing. With a typical aircraft signals, let's now look at the distribution of altitudes of all the aircraft's messages, all 150 million of them. Let's pull out the 5%, 10%, 25, median, 75, 90 and 95% percentiles using the percentile cont function. For the more observant of you, you will of course have spotted the deliberate mistake. I managed to get the 5% percentile wrong. Here I have asked for the 50% percentile, which will hopefully return the same value as the median. An extra point if you got that right. So from here we can see that the minimum altitude recorded was minus 375 feet with a maximum of 124,400. Vertica's detect outliers function creates a view over a base table containing the outliers within the data. These outliers are identified using a robust z-score method and an outlier threshold. The threshold representing a value beyond which a data point becomes an outlier. Here we can see that of the 150 million message tree rows that we identified earlier, 1.7 million have been identified as outliers. That's just over 1%. Looking at the number of messages that were received at the lower end of the outlier set, these are in the low 100s of records with an altitudes from minus 375 feet and upwards. At the other end of the scale, there are single-digit records of aircraft reporting altitudes in the 100,000 feet range. Of course, this does not answer how outliers came about, but at least we have a simple-to-use function to exclude them from our future analytics and machine learning. Having started this project with a Raspberry Pi in my home office west of Swansea, this was fine for tracking the transatlantic flights and many of the domestic flights passing over South Wales, but with not many aircraft taking off or landing in Swansea International Airport, I wanted to set up a facility slightly closer to a larger airport. Thus, with the opportunity to set up one of these in our data centers in Geneva, I naturally jumped at the chance, so I now have a receiver just a couple of kilometers from Geneva Airport. Installed and operational from July 2017, I repeated some of the visualizations that I had prepared earlier. Though noting from the screenshot on the right, we are again seeing quite a distinctive pattern whereby the northwest and southeast radio signals are not being picked up as much as those to the southwest and the northeast. Then, considering that there are some small mountains, such as the Matterhorn with its 4,500 meter elevation, and other such prominent obstacles, it's no wonder radio signals are not getting through. Maybe I should have sited this receiver at Schiphol in Amsterdam, though then I might have legitimately seen aircraft flying below sea level, as the elevation of their airport is minus 11 feet. In the 58 days up until I captured this screenshot, the Geneva receiver had captured and recorded 1 billion messages from 12,000 distinct aircraft over an area of approximately 200,000 square kilometers. Though, let's start with just one of the 12,000 aircraft. The one I chose was an 18-year-old British Airways Airbus A319. I know in that in the 58 days of observations it had landed and taken off from Geneva and had also flown overhead en route to somewhere else. Of note is the Mode S or hex ident of 400801. Taking a closer look at these Type 3 messages, by issuing a count star on the aircraft registration number, there are approximately 14,000 messages. As we can see, of the 14,000 messages, the first set of messages were seen around 1338 on the 21st of July up until 1348, where we had received 68 of these Type 3 messages. These messages appeared sometimes every second, sometimes several seconds apart. It also looks as though this aircraft is climbing as the altitude is increasing, starting at 16,100 feet when it was first observed through to 35,375 feet when it disappeared off the face of the Earth. But seriously, that was the point it presumably went out of range of the radio receiver. Then there is a break, with the next messages for this aircraft being received 3 days later on the 24th of July starting at 22:23. Though this time, with an altitude decreasing, one can presume it is coming in to land. Using one of the visualization tools, let's plot the tracks of this aircraft over the 58 days. Zooming in, although it is possible to make out the general track of each flight, there are clearly gaps in the tracks due to the sporadic nature of the messages being received. Those messages being received close to the antenna in Geneva are clearly more frequent than those from further afield. Using Vertica's time series clause, we can define a time slice here set to 1 second to calculate a generated column based on the sorted timestamp column partitioned by each aircraft's hex ident, although in this instance for just the one plane as defined in the where clause. In addition to defining the 1 second time slice, we are using the TS first value function to calculate the values for altitude, latitude and longitude based on a linear scaling from the associated value at the start of each time slice. These derived values are being returned as columns called GFI altitude, GFI latitude and GFI longitude, noting here that I have chosen to cast the GFI altitude to be an integer. We can see here that we now have rows for each second with derived values for altitude, latitude and longitude. As mentioned earlier, these are based on the linear scaling between the previous and next recorded values. Initial thoughts are that this is just what we wanted, rows for every second. However, as you may recall from the raw data seen earlier, that data had a gap between 1348 on the 21st of July and 22:23 on the 24th of July. Unfortunately, our GFI has also filled in all the missing values between the 21st and the 24th of July. Vertica had not realized that although this is the same aircraft, it is clearly not on the same flight. As we saw on the previous slide, we now need to find a way of separating the sets of rows for each flight of the same aircraft. In this snippet of code, we are introducing the conditional true event function to assign an integer starting at 0 to a derived column, in this example called flight. Making the presumption that a plane cannot land, taxi, park, unload, refuel, reload, taxi and take off in less than 1 hour, I have set the gap for the conditional true event to be greater than 1 hour. Thus, if the current timestamp is greater than 1 hour to the previously observed timestamp, we will presume that the current row is the first of a new flight or session and will increment the flight column by 1. Where the timestamp of the current row is not greater than 1 hour after the previously observed timestamp, we will presume that this is the same flight. Slotting this snippet of code into our previous GFI code, as we can see here, the new flight column on the right groups together all of the rows for a single flight for this aircraft. We now have flight 0, with rows for every second from 1338 on the 21st of July through to 1348 on the same day. Then, as the gap between this timestamp and the next is over 1 hour, the flight number for the flight on the 24th of July for this same aircraft is flight 1. Scanning through the whole 14,000 messages for this aircraft, we can see that there are 45 separate flights recorded between the 21st of July and the 7th of September. Referring back to our original representation of flights tracked for this aircraft, where there were obvious gaps in the tracks due to missing messages, especially when the aircraft was further away from the antenna and receiver. With gap filling and interpolation and sessionization applied to that same data, we can now see that the tracks are much clearer. And with the addition of the flight or session column, we can now differentiate the different flights of this aircraft, demonstrated here by the use of color coding. As mentioned at the outset, this journey of the lab series and the particular mini project has only just begun. We have hardly touched on the advanced analytics and machine learning built into Vertica, nor looked at the many other capabilities from capturing and enriching, measuring and preparing, and modeling and deploying our data. How far this project continues will be determined by the members of the Big Data and Machine Learning Meetup. As new projects get proposed, or this morphs into other projects, who knows where this may take us. If you want to follow this project or start up something totally new, sign up for one of the meetups in London, Munich or Cambridge to find out more. In the meantime, please do not hesitate to reach out to me. My name is Mark Worley. Thank you very much.
Look, Mummy, there's no plane up in the sky.
Jersey 9 November Victor, runway 27 clear to land, wind 27018, question 32.
Still on 37, Jersey 9 November Victor.
Emirates 1 vooruit, hello, behind Air France, line up 24 Sierra 7 behind.
Behind the Air France, line up runway 24 behind Emirates 148.